So I will start with an introduction about myself. I am José Valim. I am co-founder of Plataforma Tech. We are a consultancy based in Brazil, but we work with Ruby on Rails and companies around the world. And you probably know me and Plataforma Tech because of our open source projects like Devise, Simple Form, our contributions to Rails. I am part of Rails core team member, and I wrote this book, Crafting Rails Applications, which talks about Rails internals and how to understand and use Rails better. So, but today I'm not talking about Rails. I'm not talking even specifically about Ruby. I'm going to talk about concurrency in general and try to give you an overview of why is it changing, why concurrency is becoming a more and more popular subject, right? And where are different languages going, right? So I want to give you an overview so everyone can explore more about the subject later. And I'm going with a very simple definition of concurrency, which is to execute several tasks simultaneously, right? So a very simple example, imagine you have a CSV file, right? And you have a column that is a value, and you want the total of summing all rows, okay? If the file is very big, it can take a lot of time. So you can simply say, I'm going to break this file in two, and I'm going to calculate this value for this half and for this half, and you do that at the same time, and then you're going to have the value of each half, sum them, right? So this is a very simple concurrency. You're breaking the file in two, calculating the halves simultaneously, and that's it, right? This is an example of concurrency. One example that we Rails developers will be more familiar is this one. If we're using Passenger, for example, one of the ways for you to deploy your Rails application is that you have a configuration in Passenger that say, hey, when I deploy my application, I want Passenger to start like 5 Rails instances, right? So we are going to have like 4 or 5 servers. And this is also a way of doing concurrency, right? We call multi-processes concurrency because we have many processes. But this kind of concurrency, I'm not going to talk about it today because as you can see here, if I have 4 cores, I need to start 4 processes to use all the cores on my machine. And that's bad because what I'm thinking about is that in the future, we may want to deploy our software in a machine with 16 cores, right? And you don't want to start like 16 Rails instances, right? Or 24. Today, my machine has 4 cores already. It's going to increase for sure in the future. It's easy for you to get a server that's going to have 16 or 24 cores. So I am talking specifically today about this kind of concurrency, right? You want to have a server, you want to have a process, and it's going to use all cores in your machine. So we say it's single process, multi-core concurrency, okay? So, but before eventually talking about concurrency, I want to go back. We're going to go to a magic world where we have no state and we don't have concurrency as well. And we usually call this the declarative model, right? And it's heavily based on mathematics because you can do pretty much the same thing, you can do mathematics. So what do we have here? What we don't have mutation. So we don't have a state, we cannot mutate stuff. When I say you cannot mutate stuff, you can think like in Ruby you have an array, right? And you can append an element to this array. And the array changes, so the array mutated. We cannot do that here, right? If you have an array and if you want to append an element, you're going to have a new array with that element. You never mutate things in place. You always create new ones. So you don't have concurrency as well, and everything, they are just functions, which in Ruby we can say that they are lambdas, right? So what we can do, we can define a factorial function that it's going to receive a value x, and if x is 0, we are going to return 1, which is the value of the factorial 0. And if it's not 0, we are going to call the factorial recursively, right? And you're going to get the final result. If we executed this code, you're going to get the factorial of 10, which is and the correct result. And that's what we can do. We can do that. We can express like mathematical functions like Fibonacci, factorials. We can do list manipulation, text manipulation, maybe some artificial intelligence stuff. but we cannot do much. Because when we are in the declarative model, we say that everything is deterministic. And this is the important point. Because if you're in the declarative model, our software is going to have specific characteristics that it's important for the machine. So by determinism, I'm saying that the same input, so when I call a function, when I call a method, the same input always needs to give me back the same output. This means that we can't have I/O, right? Because when you say file.read full, you can get different results. The parameter is the same, it's always full, but you can get different results, right? Because you read the file once, and then you get some contents, and then someone changed the contents of the file. You're calling the same function, the same input, and somehow you're getting a different output, right? So you cannot do that. You cannot do I/O in this deterministic declarative world, right? You cannot do random, right, by definition, because random, every time you call it, you get a different result back. So you can do that here as well. In general, we say that everything in our code has no side effects, right? So we live in this world where there is no way I'm going to call a function, and this function is going to change the result of the other function, because everything is deterministic. The same input, always the same output. So we cannot write to the database too, right? Because, for example, in Rails, when you create a new record, when you save something to the database, you are changing the result of post.all, which is returning all posts from the database. So everything is deterministic, always return the same result for the same input. We have no side effects. And why does matter, right? So imagine that we have this code. We have a lambda, a function. It receives two arguments, A and B. And we calculate the value of C in function of an expensive function. And then we calculate the value of D too, right? Which is calling another expensive function, right? And we add C with D, right? This is a very simple function. And now here's the interesting part. If this code is deterministic, right? If there are no side effects, we can do, the language runtime can do a lot of cool stuff with it, right? So let's suppose that we put this code live in production, right? It's running, and let's suppose that 80% of the time, it happens that A is equal 1. Like almost all the time, A is equal 1. So what is happening here is that you are calculating the value of expensive function for 1 all the time, right? And that's unnecessary. You're calculating it over and over again. So your language runtime, you don't need to do anything. Your language runtime is going to say, you know what? I know that every time that A is equal 1, the result of expensive function is 42. So I'm just going to replace it. I'm going to optimize it for you, right? I'm just going to do this hot path here. So I'm not going to call expensive function anymore. And why it can do that? Exactly because it's deterministic. We don't have side effects. There is no way that calling or not calling expensive function is going to change the properties of our system, right? It cannot do side effects. It cannot affect anything, okay? So this is great, right? The machine can do a lot of work for us. Something else that we could do is that if we have the same function, and for some reason, the machine decides, you know, if I call also expensive first the expensive function, it's going to be faster. The machine can do it, right? It can just swap the order of the expressions. And this happens, right? C compilers, they say that they may change the order of something to do specific optimizations, right? So the language can just, you know, I'm just going to swap the order here and everything's going to be fine, exactly because you don't have side effects, right? This seems like very distant, but there is a language called Haskell. Who already programmed or read something about Haskell? Yeah, a lot of hands. I don't like Haskell, but you can like it. What happens here is, in Haskell, you separate all determinist code from non-determinist code. And it not only helps in performance, but it allows the language to be more expressive in different ways, because it can just optimize and organize the expressions when the code is deterministic. So it's very interesting application of what we're talking so far. Okay, so that's the beautiful world, right? And I want to show you that what's going to happen if we turn concurrency on in this beautiful world. So we have state off, but concurrency is on now, and we have a type of concurrency which is called data flow variables, right? And how does it work? We have that same code, right? Our lambda that receives two arguments, expensive function, and also expensive. And since those functions, they are expensive, you want to calculate them simultaneously, right? You don't want to calculate C and then calculate D. You want to calculate both at the same time. So what we're going to do, we are going to use our friend's thread, right? So what I'm going to do here is that I'm just saying, like, you know, I want to calculate the value of C in a thread. I want to calculate the value of D in another thread, and that's it. And if you do that, your code's going to work. Just this, right? This is the moment where you should stand up, point your finger at me, and say you're lying, right? Because the last time we've worked with threads, it was not that easy, right? We had to change our code somehow. Sometimes the system was starting to work strangely. Sometimes the test passed, sometimes the tests were not passing. There were bugs in production that were just happening in the peak hours. So thread was not that easy, right? But why it's easy here? Because there is no mutation. There is nothing shared. Everything is deterministic. And again, the language runtime can do a lot of hard work for us. For example, what's going to happen here? We are going to start the Lambda, and then when we start the Lambda, we are going to spawn a new thread, right? The thread is going to execute and calculate the value of C. And then the next instruction is to start another thread that's going to calculate the value of D. So you have the value of C and D calculating simultaneously. And then you're going to reach the point where you need the value of C, so you can add C with D, right? And when you reach this point, the language knows, I know that I don't have C yet, but I know that the thread is calculating it, so I'm just going to wait for it. So how does it work? Again, we start with the main, right? The main path of execution. And then the first thing we do is to spawn thread 1. And then the second thing is to spawn thread 2. And then we're going to add C with D, right? But then we realize that C was not defined yet. The runtime says, it's okay, I know it's not defined, but I know it will be ready eventually. So I'm just going to wait. We don't need to do anything on our own. The language is doing that for us. So I'm just going to wait. And when thread 1 defines C, the main say, oh, now I need the value of D. And then it waits until D is defined and add C with D. And it works. We just need to say, I want you to calculate this concurrently, right? And this is not very far because there is a software that unfortunately we have to use from time to time that works very similarly. It just don't have the concurrency, but has the same idea, which is Excel, right? Sometimes we create the formula, and there is this field that depends on the other field that depends on the other field, but Excel can figure out all the dependencies and know which one to calculate first, which one you should calculate next. It's the same idea. It's data flow variables, right? You can think, when you think about Excel, it's clear, right? Because we can easily imagine that the data is flowing, the values are flowing, and you get the final result properly. Okay, so this is good, right? The main point of showing this is I just want to show, like, if you don't have mutation, if you don't have state, how easy it is for you to have concurrency and to work with threads, right? It just works. So, but it doesn't help us much, right? Because we still don't have I/O, so we cannot read a file, we cannot print something in console, we cannot talk to the database, we cannot write something to a socket. We cannot create a web application, for example, right? So we need to turn state on, and both the internal state, the outside state, we need to have side effects, right? Because we want to build all this kind of stuff. And then we have the point where we have state and concurrency on, and that's when things go bad, right? So what is the problem? We are going to show the problem that happens with this very simple example. So it's going to show what happens when you have state and concurrency. So here I have a class counter which has an accessor, right? And I can access this accessor as counter.i. And this accessor, it's shared, right? It's global. Anywhere in my code, I can access it. I can change its value, right? It's shared. It's global. It's shared memory. It's shared state, right? So imagine that our software, we have this counter, and we have a lot of threads, right? We have a lot of things that we are doing simultaneously, and at some point in those threads, we are incrementing the value of counter, right? And we do that in 3 steps. First, we need to read the value of the counter. So we read, we increment it by 1, and then we set it back. So it's 3 steps. We read it, increment it by 1, and set it back. And what happens when we run this code with many threads is this. We start with the counter I with the value of 0. We are going to read it, increment it, and set it back. So a thread read it, increment it, and set it back. Okay, good. And then the thread 2 eventually is going to read it too, right? But this is the thing about threads, right? You don't control your execution. So the thread can start running and just say, you know what, I'm going to stop. And then another thread is going to pick up, right? So the fact that by default we don't control their execution, right, by default, it means that the thread 2 can simply stop, it just read the value and it stopped, it did not finish, right? And then the thread 1 is going to pick it up, the value again. Since the thread 2 didn't change it, the value is still 1. And then the thread 1 is going to read it, increment it, and set it back, right? And then it stopped, and then the thread 2 says, you know what, I'm going to finish. And when the thread 2 wants to finish, they already read the value. They're just going to increment it and set it back. And now we have a final value of 2, right? When it was supposed to be 3, right? Because we executed that 3 times. So this is a very simple example. It's race conditions that happens when you're using threads, okay? So how we can solve that, right? That's the most important part of the talk now, which is different languages. Since concurrency is becoming more and more important, we are starting to see different solutions to this problem, right? The solution that everyone is using, not everyone, but most of the people are using today, are using some kind of mutex, some kind of lock, some kind of condition variable to solve this problem. And different solutions that are popping up, right? So I want to discuss them. So we have 2 categories, right? One is shared memory concurrent model, which is exactly what we just saw. We had a shared memory, which is counter I, and we can solve it in 2 ways, which is using locks. And the another way is transactional memory. And we have another category, which is message passing concurrent model. Okay, so let's start with locks, which is the most used one, okay? So how it works, we have this code, right? We have our counter, and we have our counter I, and we have the thread, right? The basic solution we think when we have this problem is that, you know what, so to solve this problem, the most intuitive solution is just to say, although the threads, they are executing a lot of stuff, when it gets to this part, we could ensure that just one thread is running this at the same time. So if you have like 100 threads, when it comes to this part, just one thread can do it, right? Just one thread can run it. So here I'm expressing that using a synchronized lock, right? And that's basically saying just one thread is running this piece of code at the same time. How this is going to work then? We start with the counter with value equals 0 again. The thread 1 is going to read it, increment it, and set it back, right? And then the thread 2 is going to read it, and when it reads it, before it starts the synchronized block, right? And this means now that even if the thread 2 is stopped, all the other threads in our software can do a bunch of work, but they're never going to reach this part where they read, increment, and set the value back. We have that guaranteed. So we know that even if the thread 2 stops, it's going to eventually, hopefully, right, come back, right, increment the value, and set it back. So now we can guarantee that it works. And then the thread 1 can eventually go to this piece of code again, read it, increment it, and set it back. Okay? So it works. We just put a lock, and we said, okay, this can be run just by one thread at the same time. What are the advantages of this approach? It's the most popular approach, okay? And this has very simple semantics, and those semantics are based on giving us explicit control over the lock. We are the developers, we go to that piece of code and say, hey, I'm putting the lock here, right? But this is good, but it's also very bad because who has to put the lock? Us, right, the developers. And we make mistakes, we forget to put the lock, or we sometimes simply don't notice that we have a race condition there. So this is bad, right? And those concurrency problems, they're not necessarily easy to track down. And another disadvantage is that this is a pessimistic approach, right? What I mean by that is that if our software has like 1,000 threads, we are saying just one can run that piece of code at the same time. Maybe it was fine if like 100 threads run that piece of code at the same time, but they're saying, no, 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 no. Everyone stop, just one, okay? So it's pessimistic. So this led to this other solution, which is called software transactional memory, which was made popular lately by Clojure, right? And how does it work is that we are going to slightly change our solution here. Now we have the class counter again, and our accessor I now is not just 0. We are saying that our accessor I is a reference. So I use the reference there. It's pseudo Ruby code, but we have that reference there. And the thing about references is that you can just change a reference inside the atomic block, right? So this already helps us, because if you try to play with this reference outside of atomic block, you're going to get or a compilation error or a runtime error. So this is already better, right? We are saying, no, I have this special thing that I can just mutate it on those special places. And then when we come here, we have the atomic block because we want to set the value of I. So let me just grab some water. This software transactional memory thing is very similar to how databases work, right? Transactions in the database, as we're going to see. So how does it work? Again, we start with our counter I equals 0. The thread 1 is going to read it, increment it, and set it back. And then the thread 2 is going to start the atomic block and read it, right? And now it's the same story. The thread 2 read the value, but it had to stop. It stopped, right? And then the thread 1 is going to read the value, increment, and set it back, okay? And then the thread 2 is going to start again. Since the thread 2 already read the value, it's simply going to increment it and try to set it back, right? But at the moment you try to set it back, we finish the atomic block. And what the atomic block is going to do is, it's going to ask, did someone change the value of the reference while I was calculating it? So it's basically going to compare the value of the counter I before the atomic block and the value of counter I when the block's closing, right? And it sees that the value is different. So it says, whoa, I cannot commit this operation, right? Because someone changed the value. Someone changed the value of counter Y while I was doing my stuff, while I was doing my calculations, right? So what the atomic block is going to say is that it's going to do a rollback, right? It's going to start all over again. And now when it starts all over again, it can potentially read the value, increment it, and set it back. So now we have, again, the proper result of 3, okay, which is what we expected. So what are the advantages of this approach? It's an optimistic approach, because we are saying, you know what? All the threads can run that piece of code, and eventually if there's a conflict, I'm going to detect it and start over again. So everyone can just run it, right? I'm fine. And the different implementations can guarantee that you're not going to have deadlocks or race conditions, right? Because what happens in the lock scenario, which was the previous example, we had a lot of threads that was waiting on one specific thread, right? So it could happen that we have this thread, that it's waiting on this thread, that it's waiting on this thread, that it's waiting on the original thread, and then you have a deadlock, right? Everyone is waiting on everyone, and that's not going to get solved. Here, that cannot happen, right? But as everything, it also has disadvantages, right? What are the disadvantages? Potential unnecessary retries. It could happen that every time that the thread 2 wants to commit the block, someone changes the value of counter I. And then the thread 2 starts over again, and then someone changes the value of the counter I. So the thread 2 is running that piece of code all over and over again, and it cannot actually commit it, right? This also happens in databases, right? If you have an auction website or something like that, you can potentially go into situations where this is happening, right? You have a lot of people trying to commit at the same time, and you're always blocking others, and so it never gets committed. So we have these potential necessary tries, and there is the whole transaction overhead, because now you have those references. You need to keep the value of the references before each block. You need to compare the blocks. So it's, there is this overhead. It's also semantically a little bit more complicated, right? Okay. So that was about shared memory concurrent model. Again, it was shared memory because we had that counter I that was shared, it was global, everyone could access it. Okay? Now we are going to another approach of solving this problem, which is message passing concurrent model, which is my favorite. And here, we don't have shared memory anymore, which already helps a lot to solve this problem, right? We don't have that shared memory. Here, if you want to have state, if you want to have a counter, for example, the counter I, it needs to be encapsulated by an entity, okay? So here's an example. We have a server, and this server is basically a function, right? It's a lambda, which has our counter I now. It's a parameter of that lambda. And what is going to happen here is the following. This lambda, here I'm using again pseudo Ruby, right? Because we have this special keyword called receive. And what receive is going to do is that it is going to block the server until it receives a message, right? So at the moment we enter receive, the server is a thread that's going to stop. It's going to wait. And then it's going to receive a message. If the message is increment, is the symbol increment, what is going to happen here is that we see like, oh, I got the increment message, which means I need to increment the value of the counter I and start the server over again. I need to call the server over again. It's recursive, right? And then when I call this function, the server function once again, I'm going to wait for another message, right? So basically what is happening here, we have the server that it's waiting for messages, and when a message comes, it does something, right? It reacts to the message and enters in the loop again to wait for the next message. And then it enters in the loop again to wait for the next message. So, for example, again, if we receive the message increment, we are going to increment the value and start it over again, right? If we receive the message check, it means that whoever sent us the message wants to know the value of the counter. So I'm using that arrow to the left to say that I'm sending the value to the client, and then I start the server again to wait for the next message, right? And if I eventually receive a message that I don't know, I can just print like, oh, I don't know which message this is, and then wait for the next one. And then I start my server here at the bottom with the value of the counter equals to 0, right? So this is the important thing here. We no longer have this shared thing, right? Our state is encapsulated by the server, and if you want to change it, you need to ask the server to do so, okay? So how our client looks like, our client is going to be threads, okay? And they're going to do a lot of calculation, and every time they want to increment it, they are going to send a message to the server and say, hey server, increment that counter, okay? So how does it work? We have the server, it starts with the value of 0, and then the thread 1 sends the increment message, right? And then it increments it by 1, and then it sends another message, it increments it to 2, and here we go, right? And then the thread 2 sends a message as well, it goes to 3, and then if we eventually want to know the value of the counter, we can send a check message, and we are going to receive the value back, right? So that's it. Why this approach is interesting? First, there's no need for synchronization anymore, right? We don't need to put atomic block, we don't need to put synchronized block. Synchronization is gone, right? And my favorite thing about this approach is that it's easy to distribute because everything is built on this idea of message passing, right? So the language implementation of or the feature implementation, the library implementation, they can say, actually, it doesn't matter if the server is in this machine and the client is on the other machine, right? The library can abstract that all for us. So you can start with your first version of the code running with the server and the clients all on the same machine. But if you say, I need more machine, I need more power, right? You can just put the clients in other nodes in your network and it's going to work. We say that this is location transparency, right? You can build location transparency into message passing, and you can distribute it because all we are doing is sending messages, and the library can handle where the server is and where each client is. right? So this is nice. This is very nice. Disadvantages. Everything has advantages. Coordination may be tricky, which I mean by that is that if you need two clients to read the value of the counter at the same time, this approach is not going to work, right? Because you cannot do that. You cannot cheat, right? If you want to know what is the value of the counter, you need to send a message, and you need to wait for the server to give you the answer, right? So if you need different entities checking exactly at the same time what is the value there, you cannot do that, right? And it's a non-conventional approach, right? This is a weak advantage, but it is because we had to write our software in a different way, right? So that was it. Those are the ways of doing concurrency that I wanted to tell you about. I'll do a quick summary here. So we talked about data flow, and the language that has very good functioning works of data flow is a language called OS, right? So you can check it out. Locks, we have libraries for most of the programming languages out there. So we have for Ruby, Java, C. So if you want to know more about locks, you can check out Ruby Standard Library. We have software transactional memory, right, which was made popular by Clojure. And message passing, we have Go, which is a language created by Google. And we have Erlang too. They both use message passing, but a little bit different. Go uses the idea of channels, and Erlang uses the idea of actors, which is more similar to the example I just showed you, right? And if you don't want to go very far, if you want to study more about concurrency without necessarily changing to another language, there's a project called Celluloid. I don't know if Tony is here, but Celluloid, it's a project that brings message passing, brings actor model, similar to what we saw, to Ruby, right? It also has the idea, there is a project with Celluloid called Decel that implements the whole idea of distributed location transparency too, right? So if you want to play a little bit with the actor model in Ruby, you can try this out. There is a language also called Elixir, which I am developing with the folks at Plataforma Tech, that is built for the Erlang virtual machine. Who already built something with Erlang or tried to write something with it? Yeah, okay. So some people, sometimes they have bad experience with Erlang. They don't like the syntax, they cannot grasp it. So Elixir is another way to expose their Erlang virtual machine with a syntax that's going to be certainly more familiar to us. So that's the idea of Elixir. And I want to say for last some final considerations that defaults matter, right? So what happened is that when we first started with computers, memory was like expensive, and we had very little memory. So it made sense in that time that if you want to change an array, right, you would just change that array in memory, right? If you want to like change the value of the element in the array, you just go there and change that value in memory directly, right? Because that was the most appropriate thing to do. But today, memory is cheap, right? And we say that the free lunch is over, right? The CPU is not getting much faster anymore. If you want faster CPUs, we're starting to have more and more cores on our machine, right? So it's changing, right? So basically, we had one core before, expensive memory, so it made sense to change things in memory. Now, memory is very cheap, and we have a lot of CPUs. So this idea of changing the things in memory, it starts to be a bad idea, right? Because that's when the issue comes, when you have state, when you can change things, when you have mutation, when you have state, right? So this is changing. And I'm saying that defaults matter because languages like Erlang and Clojure, they default everything to immutable, right? So if you have an array, a list, and you want to add a new element to the list, you are creating another list. You're not mutating that list in place, right? So, and since if we do that, we reduce mutation, and then write concurrent software becomes much easier, right? But a full having default to immutable is a good idea. In general, I like to say there's no magic bullet. I think that us as a community, we should not say, I want that solution, right? It would be nice if we could have different solutions and be able to choose which one's the best based on the problem we are trying to solve. Okay. So a few references. There is this amazing book called 7 Languages in 7 Weeks. And they talk about Clojure, they talk about Erlang, I think they talk about Haskell too. So if you want to learn very quickly those different languages and understand a little bit more about the concurrence paradigms that they bring, this is a very good book. If you want to go a little bit more academical, there is this excellent book called Concepts, Techniques, and Models of Computer Programming. Okay? And more lightweight reading, there is this very good article. I'm going to put the slides online so you can be able to pick the addresses from there. Called this article, Software Transactional Memory, which explains how Clojure works. And it also mentions about locks. It does a little bit of comparisons too. And there is this talk about persistent data structures from Clojure's creator, Richie Hickey. Did I say his name correctly? Is Richie Hickey or Richie Hickey? I never know. Hickey. Okay, thank you. So you can think, right? If every time, if everything is immutable, it means if I have a list and I want to add a new element, I get a new list, right? So you can say, whoa, isn't that like bad? If I have a list with like 10,000 elements and I want to add a new one, I'm going to have to copy everything and add the new element, right? So this talk is about how Clojure implements it in a very performatic way, right? Without having to copy the whole list. So it's a very interesting talk. So that's it. Thank you very much. I'm going to open the space for questions if you have time. And I just want to say that I have some stickers with the Hacking Beautiful code. So if you want, there's some in the reception. Come grab with me, and that's it. Thank you. Do you have time for questions?
Yeah, a couple questions.
Yeah, so let's do questions. Yes.
In the message passing, you're kind of building an isolated box, right? And that all goes synchronously, is that correct?
So the question is if in the message passing we are creating an isolated box and you're running it synchronously. No, so the idea is that you have the server running in a thread, right? And the client's running a thread. Usually when you have message passing by actors, everything is running in a thread. Go has the idea of Go routines. So basically the idea is that almost everything is running concurrently, and then you can exchange messages with all those things, either synchronously, you get the idea, and asynchronously. More questions? Okay. Yeah, so the question is about Ruby. And so in Ruby, we have locks by default in the standard library. And if your question is about specifically the message passing, is that correct? Or?
Yeah, so if you said, I want some that I don't care if it's different things, at the end of the day, I have them together if it's real.
Okay.
Could you send messages to separate servers available?
I'm not, so the question is about the servers and the design approach of breaking and calculating into two halves, right, and summing everything. So if you are talking, so I'm going to talk about locks, which is how you would do it in Ruby by default. So you need to synchronize the threads and put a lock when you get the results and have them communicating somehow. But if you're talking about the servers, then you have to use Celluloid. And I think you can do it distributed. We need to check with Tony. He's here at the conference. I just don't know if he has arrived yet. And we can probably design it in a way that you just send a message and it's going to find the available server or whatever that's going to do the compilation for you. But then it goes to the specific implementation of Celluloid and how it works. Okay? Thank you.